In the high-octane world of racing, speed is everything. But raw power means nothing without control, and control begins with the frame. This isn't just a skeleton. It's a weapon of precision, a masterpiece of engineering, and the first line of defense when things go wrong. Every corner, every collision, every millisecond depends on it. So how do you build something that's light enough to fly, yet strong enough to survive a 200-mile-per-hour crash? Welcome to the world of racing car frames, where steel, aluminum, and carbon fiber are sculpted into machines of velocity, where design isn't just for speed, but survival, and where every joint, angle, and weld has a purpose. In this documentary, we'll take you behind the scenes of one of the most advanced racing workshops on Earth. From digital blueprint to crash-tested perfection, this is how a racing car frame is made. Before a single weld is made, before a single fiber is laid, every racing car frame begins as a virtual blueprint. Engineers use advanced CAD software, computer-aided design, to map every curve, every joint, every load-bearing point. But this isn't just about shape, it's about forces. That's where Finite Element Analysis, or FEA, comes in. FEA breaks the frame into thousands of virtual pieces, allowing engineers to simulate the stresses of real-world racing. High-speed turns, sudden braking, direct impact. Every scenario is tested digitally before any metal is touched. The goal, maximum rigidity with minimum weight. Because in racing, even a few grams can mean the difference between first and forgotten. Now comes the question of materials. Most high-end racing frames fall into two categories. 1. Tubular space frames, made from steel or aluminum alloy tubes. 2. Monocoque chassis, made from carbon fiber composites. Chromoly steel, short for chromium molybdenum, is a favorite for its strength and weldability. It's heavier than aluminum, but far tougher under impact. Aluminum alloys, on the other hand, offer weight savings, critical in categories like Formula E or electric prototype racing. But welding aluminum requires precision, and it's more prone to fatigue if done wrong. Then there's carbon fiber, the crown jewel of motorsport engineering. Light as plastic, strong as steel. When layered and cured properly, it forms a rigid monocoque shell that absorbs impact and resists flex under extreme pressure. But carbon isn't easy. Each fiber must be laid by hand or guided by automated robots, layer by layer, according to strict orientation patterns. Then it's baked under vacuum and pressure in an autoclave to form a single, seamless piece. Every design choice is a trade-off. Weight versus strength, flexibility versus rigidity, speed versus safety. But the result is a frame that doesn't just hold parts together, it defines how the car feels, responds, and protects. Next up, we leave the screen behind and head to the shop floor, where raw metal is bent, cut, and welded into the real shape of speed. From blueprint to reality, the design is done, the materials selected, now it's time to build. In a racing workshop, the shop floor is a symphony of sparks, heat, and precision. And at the heart of it all is the frame, coming to life one cut, one weld at a time. For tubular frames, the process starts with raw metal tubes, usually chromoly steel or 7000 series aluminum. Each tube arrives straight and uncut until it meets the CNC cutter. These high-precision machines don't just slice, they notch, cope, and angle the ends of tubes so they fit together perfectly, like puzzle pieces. Because when it comes to race cars, fit isn't just aesthetic, it's structural. Meanwhile, jigs, custom fixtures built from steel, hold every piece in perfect position. No tube is welded freehand. The entire frame is assembled within the jig, ensuring exact geometry. Suspension pickup points, engine mounts, and roll cage all align within fractions of a millimeter. Now comes the welding. TIG welding, short for tungsten inert gas, is the method of choice. It's slow, deliberate, and incredibly strong. A skilled TIG welder becomes an artist, laying down beads as smooth as stitching on a racing suit. For aluminum frames, the stakes are even higher. Aluminum doesn't show heat like steel. If it's overheated, it weakens silently. That's why many workshops use robotic welding arms for repeatable, controlled welds, ensuring every frame meets aerospace-level tolerances. Each joint is critical. In racing, a single bad weld can mean catastrophic failure at 200 miles per hour. But what about carbon fiber monocoques? That's a different world entirely. Instead of welding, carbon fiber frames are laid up in negative molds. Technicians carefully place sheets of woven carbon, each aligned to handle a specific directional force. Some parts are reinforced with Kevlar or aluminum honeycomb to improve crash resistance without adding bulk. Once the layup is complete, the mold is sealed in a vacuum bag, then baked in an autoclave, a giant pressurized oven that cures the composite into a single unified shell. The result? A monocoque that's light, rigid, and incredibly strong. The kind of frame that can carry a Formula car at full speed and still protect the driver in a rollover crash. Whether it's steel tubes or carbon fiber sheets, the same principle applies. Perfection is the only option. After fabrication, the frame isn't painted just yet. First, it's cleaned, inspected, and tested, because even the smallest defect could lead to disaster on the track. Coming up next, we'll see how every weld is checked, every angle verified, and every frame pushed to the limits, long before it ever hits the starting grid. Before any frame hits the track, it must prove itself, under scrutiny. Every weld is inspected using ultrasonic testing or X-ray scans to detect hidden flaws, because in motorsport, a tiny crack could mean total failure. Next, laser measurement systems map the frame's geometry in 3D, verifying that all mounting points, engine, suspension, safety cage, align with engineering specs down to the millimeter. Once cleared, the frame moves to the integration phase. For tubular frames, brackets, mounts, and reinforcements are installed. For carbon monocoques, threaded inserts and aluminum components are bonded into the composite structure. Every addition must be feather-light and race-strong. Stress zones, like roll hoops and impact points, receive special attention, ensuring strength without excess weight. Finally, the frame is coated, powder coating for metal, protective resin or films for composites, shielding the structure from corrosion, UV, and vibration. At this stage, the frame is more than metal or carbon. It's a calibrated platform ready to carry speed, safety, and the dreams of a racing team. Coming next, we test that strength, pushing the frame through brutal simulations and safety trials no ordinary car would survive. It may look finished, but this frame hasn't earned the right to race. Not yet. Before it's allowed near an engine or track, it must survive the unforgiving world of structural testing. First up, torsional rigidity. The frame is clamped at one end while the other is twisted under load, simulating the forces a car experiences during high-speed cornering. Sensors record how much the frame flexes under torque. Too much flex, the car will feel unstable and lose performance. Too little, it may crack under pressure. Balance is everything. Next, crash simulation. Using both computer models and physical rigs, engineers simulate head-on impacts, side collisions, and rollovers. Carbon fiber monocoques are slammed into barriers at over 100 km per hour, instrumented with strain gauges, high-speed cameras, and pressure sensors. For steel or aluminum frames, crash sleds and hydraulic rams apply thousands of pounds of force to test deformation patterns. The goal isn't just survival, it's energy absorption. In modern racing, frames are designed not only to resist impact, but to deform in controlled ways, redirecting energy away from the driver. Some critical zones, like the survival cell or driver capsule, must remain completely intact. These areas are reinforced with carbon fiber weaves, foam cores, or honeycomb structures, engineered to withstand crushing loads without collapsing. After crash testing comes FIA homologation. The frame must meet strict international safety standards set by motorsport governing bodies. It's tested for side intrusion, rollover resistance, and front-rear crash loads. Each test has a pass-fail threshold. If the frame fails even one, it's back to redesign, rebuild, and retest. But once it passes, it earns something priceless: certification. Stamped, logged, and serialized, it's now an approved chassis, eligible to compete on the world's biggest stages. Finally, one last round of non-destructive testing confirms there's no hidden fatigue from the brutal trials. This ensures that what passed the lab will survive the track. From a virtual model to a crash-tested survivor, this frame has completed its journey of validation. But it still needs one more transformation: the transformation from engineered structure to racing machine. Coming up next, the final stage, assembly, finishing, and the moment this frame meets its engine, suspension, and destiny. The testing is done. The frame has survived every twist, every crush, every calculation. Now, at last, it becomes a car. In the final assembly bay, technicians move with purpose. Suspension arms, built from lightweight alloys or carbon composites, are bolted to precision mounts. The engine, often pre-assembled and dyno-tested, is lowered into place with millimetric accuracy. Drive shafts, cooling systems, electronic modules all come together around the frame. This isn't just installation, it's integration. The steering column must align perfectly with the driver's seating cell. The pedal box, fire suppression system, telemetry sensors, every system is designed around the driver and performance envelope. In formula cars, the fuel cell is mounted inside the monocoque, protected by the frame itself. In GT or endurance vehicles, modular subframes and crash structures are torqued into place with digital wrenches. Finally, the bodywork is fitted, not to decorate, but to complete the airflow system engineered into the frame's shape. Aero meets structure. Form meets function, and the frame disappears beneath the machine it supports. But its role is never forgotten, because at 320 kilometers per hour, through heat, G-force, and pressure, everything depends on what lies beneath. If you're fascinated by the machines behind the speed, subscribe to Top Discovery 4K. We bring you inside the world of engineering, craftsmanship, and innovation that fuels the fastest machines on Earth. Don't just watch the race, understand what makes it possible. Subscribe now and stay connected to the cutting edge.